Good morning, class. Last week we were calculating reactions. This week I want us to take it a step further. What do we then do after we've got all our reactions, which is the question that I'm sure everybody was asking him or herself. You've got your reactions, then what do you do? Most important thing now that you need to do is to calculate and draw the shear force diagrams and the bending moment diagram. Remember, you have a beam that is subjected to loads. So the loads are trying to find the weakest point in the beam. They will try to shear the beam. Then we talk shear force. That force there is trying to shear the beam. Then we talk shear force, and you draw a shear force diagram that is going to give you a picture throughout your beam how the forces are like in the beam. And then they will bend the beam. They will try to bend the beam. Then you talk about the bending moment diagram. Again, you draw a diagram throughout the beam that is going to give you an idea of how the moments are distributed over the beam. I hope we understand now what we need to do with our forces. Now, I'm going to start off by shear force diagram. Shear force diagram. Okay, shear force diagram. Okay, one thing, let's look at sign convention that we're going to use. If you're drawing a shear force diagram, whatever load, the loads that are going up, you're going to treat them as positive, which means the ones that are going down are going to be negative. That's the most important thing, guys, that we must always remember. If you look at the force that is going up, you're going to treat it as positive, although in real practice that is not very important. The most important thing is to be able to draw a shear force at that point. Whether you're drawing the opposite on the opposite side of the beam, shear force is not that important. The most important diagram, the signs are mainly important, when we are dealing with the bending moment diagram, because of at a later stage when you are designing now the beam, there's a different beam design for a positive moment to that of a negative moment. But when it comes to shear, shear is shear, regardless of whether it's negative or positive. But for this course, we're not going to go as far as that stage. All we're going to do for this course, just for uniformity, everybody to be on the same page, we're going to say, I don't know whether you still remember the Cartesian plane from high school, where they say there's your zero, whatever that is on this side of your y-axis is positive. That is positive. Below is negative. That's what we're going to use this day. So if, for example, you have a beam, I'm just making an example with a reaction with the force and another force here, which is in the form of a UDL, and a reaction somewhere here. So depending on the magnitude of the forces here, so you will know that this force is gonna be positive because it's going up. Between this point and that point, there is nothing happening, so you must maintain that force. If your shear, for example, here was 30, nothing is going to change nothing is going to change that shear force of 30. So you're going to maintain that shear until you get to that force, to this force. This force now is changing the whole, is destabilizing the system. So it's changing the whole thing. So what do you then do? Then you change now. You take that force into account, then you change depending again on the magnitude. Again, between this point and this point, between this point and that point, nothing is happening. Then you maintain that shear force again until you get to this point. But watch now the difference now between when you have 2-point loads and when you've got UDL. I cannot say between this point and this point there is nothing happening, because you've got a load that is uniformly distributed over the beam there. So the force here, the shear force diagram now, I cannot maintain the same shear force that I had all the way to that end. So it must change now because of the uniformly distributed load. But I will explain that again in the form of a worked example. For example, if I can think of maybe the simplest one, let me start with this one. Remember this, we did this problem, that was our first example that we did, and then we calculated our reactions at A and at B. So I am going to draw a shear force diagram for that, for this beam. Okay, there's my beam. I calculated my reaction there at A to be 18,73. I hope you still remember this. And then the load there was 18 kilonewtons. And then I had another vertical component there of 20 sine 56. Sine 56, and then I had a vertical reaction at B of 15,85 kilonewtons. Okay, I'm just explaining the shear force diagram for now, guys. Then when I'm done explaining my shear force diagram, I am going to explain how you approach a bending moment diagram. Okay, then there's my beam. Remember, positive, negative. Okay, so whatever that we do, guys, we always start at 0. The first point that you point there is 0. That's 0. We start off at 0. From 0, you've got a shear force of 18,73 kilonewtons. Go up. You don't have to measure it. You don't have to draw it to scale. That is 18,73 kilonewtons. Okay, it's going up. So between this point and this point, there is nothing happening. So I must maintain that 18,73. There's my 18,73. Please, guys, do not use freehand like me. At least you have a roller. If you don't have a roller, you have a student card. You can just use your student card to draw if you don't have a roller. But I'm allowed not to use a roller. Thank you. I still have my 18,73 at this point. Then I have 18. Remember, I said this one is positive because of the sign convention I applied there. Forces that are going up are positive, forces that are going down are negative. So I subtract now from the 18,73, I subtract 18. Obviously, I will be left with a positive answer. That means I am still on the positive side. I'm left with positive 0,87, somewhere there. 0.73. 0.73. That is my shear. Then I need to maintain that 0.73 across. Until I get to there, to this force now of 20 sine 56. I must quickly get a calculator and see if I get what is 20 sine 56. 20 sine 56 gives me 16.58. So I've got positive 0.73. I subtract 20 sine 56. There you go. 0.73 subtract 20 sine 56 gives me this answer. Give me negative 15.85. So I must, then it's on the negative side of my shear, so I must plot it negative, but 15 is somewhere there. I'm trying to draw it to scale, guys. I said 18 is 2 bars, then 15 is somewhere there, then go down on the negative. So I still have 0.73 there. Here I've got 15.85. Are you guys good? Okay, then from this point to there, nothing is happening. Maintain that until that point. When I get there, I've got negative 15.85. Then I've got positive 15.8 plus 15.85. Then what do I get? 0. Back to 0. Very important, guys. You always start at 0. You must always end at 0. That's how you must approach the shear force diagram. Shear force diagram. I hope we're happy. Now I'm gonna take the second example that we did in class. But that example, the nice thing about this example that I'm going to use now, this example is got a uniformly distributed load, which is gonna give us a different understanding of how you differentiate the two, when you've got point loads only and when you've got uniformly distributed load. Remember this example, we did this example, we calculated reactions. Remember this example, so we are doing this example now. I must quickly do it this side. This other student asked me, how many arrows must you have there? Guys, it's not important how many arrows you must have there, as long as you have showing arrows. The other student asked me, say, how many arrows must I have there for the UDL? I know sometimes you get so worried, concerned about stuff that are not really important, but it's fine. So now you know. So we calculated the reaction at A, and if it was, there's my reaction at A, 57.4. that was from there, from this, guys, there's 57.4. and then I've got my point load there of 30 kilonewtons, and then I've got my vertical reaction at B of 25.1. The load was 15 kilonewtons per meter over, again guys, I'm not drawing to scale, but please bear with me. If I use a roller, it's gonna delay me, and then I'll end up having a very huge video. but I'll try by all means to keep it sort of, yeah. Okay, now remember we're drawing shear force diagram. So there's my beam. Okay, good. Guys, you need to draw these neat, very faint. These lines must be faint. I don't want to see them because they can be very confusing if they are as bold as mine. But sometimes as lecturers we are allowed to do funny things, wrong things. Okay, always start off at 0. Remember, 0, positive, negative. I hope with that you start off at 0. So at this point your shear is 0. So 1 meter away, 1.5 meter away from that point, what is your shear? Remember, the UDL is going down. 1 meter away is going to be negative. I hope you can see what I'm typing on my calculator. 15 times 1.5. Negative is 15 times 1.5 is that distance, guys. Then that gives me negative 22. Negative 22 is there. Just plotting there, 22.5. Why am I plotting it below? Because I'm plotting it on the negative side. I hope we understand each other, guys. And then at that very same point, at 1.5, I've got a reaction of 57.4. I must add that. You see, plus. Can you see that, guys? Plus 57.4. Then I'm getting positive 34.9. Then this was 34 is somewhere there, slightly bigger than that one. 34.9. Then at this point, what is my shear at that point? Because that's the end of the UDL. The start of the UDL, I need to know what is shear at that point. There, because I've got a shear force diagram, I need to know what is shear at this. Sorry, I've got a reaction. I need to know what is shear at this point. And where you have a point load, you will normally have 2 shears at that point. If you have a point load, 2 shears at that point, which is the same thing that I did from the previous example. This you haven't noticed. At 0, I have a point load, which is my reaction, 0 and that. At 18.73 and that. And then there I've got 2 shears at that point. Here I've got 2 shears at that point. Same thing that I'm doing here. So 1 0 there. At this point, because I've got 2 shears at that point. And then if you add the 2 shears, they must give you that point load. So if I add this and that, they must give you me 57.4. Just add them, ignoring the signs now. Then they must give me 57.4. At this point, what is shear? Somewhere at this point. So I still have my positive 34.9. Then I'm going to subtract 15 times the distance of 2. Subtract 15 times 2. I'm subtracting it there. Then I've got positive 4.9. 4.9 is somewhere there. At this point is 4.9. That is, now what is happening between this point and this point? Between the 2 points, nothing is happening, so I must maintain the 4.9. Still 4.9. Then I get to this point now. Then I've got negative 30. So I still have my calculator. The 4.9 subtract 30. I've got negative 25.1. Negative 25. Hope is giving me problems. Okay, thank you. So there you go. I still have that. Then what is happening between this point and that point? Nothing. Therefore I must maintain that. So remember, there we went that route, then up, then back, sorry, straight line guys, then maintain that, then down, then across, then I've got negative 25,0 plus the reaction of 25.1. that gives me 0, so I must end at 0. That's how we draw the shear force diagram, guys. So what I expect you now to do, I expect you guys to redo the to draw a shear force diagram and bending moment diagram for all the problems, sorry, the shear force for now, for all the forces, the beams that we've been busy calculating reactions, except the triangular shaped one. The triangular shape, don't worry about that one. I will address that one if I need to address it, but I don't think it's important for this course to address how to draw a shear force and a bending moment diagram for a triangular shaped UDL. So I just wanted you to show you how you go about calculating reactions with a triangular UDL, but I don't expect you to draw the shear force and the bending moment diagram. But for this problem, I expect you to do it. Example number 5, shear force today, shear force please, shear force please, and the tutorial questions. I hope you enjoyed the video, guys. Feel free to contact me if you have problems. Thank you very much, guys. I'm feeling much better this week, by the way. Thank you. Enjoy the rest of the day. Bye.